Raga, caffè?
Hi there! We're the Sapienza Technology Team, a student group from the University of Rome, La Sapienza. Since 2016, we've been building Rover prototypes, and our main project, and best buddy, is CC8. It's a cool guy, but super demanding. That's why the team is made up of 50 students from different backgrounds, including STEM, economics, and IT sciences, organized into different specialized departments to handle every technical and non-technical need of the project. Let's break down what each department actually does. The hardware department builds the rover's body. They design and analyze the chassis, the manipulator, and the sampling systems. They work closely with the science team to make sure everything is both functional and mission-ready. The software department writes all the code that makes the rover move and think. From firmware to navigation algorithms and manipulator controls, they handle everything that involves software, especially in robotics, AI, and automation. The electronics department connects all the dots between hardware and software. This team designs the PCBs, wires up the systems, and manages communication between the rover, the drone, and the ground station. Basically, if CC8 sends signals or turns on, they've made it happen. The science department is composed of our researchers. They take care of the scientific side of the mission, analyzing samples, developing the sampling system, and writing up the reports. Their work helps the rover do real planetary science, just like on Mars. The drone department deals with our flying machine. From hardware to software to electronics, they design and build the drone from the ground up. Innovation takes flight with every circuit, line of code, and propeller. The management department is the behind-the-scenes crew. They keep everything running smoothly by handling logistics, organizing events, managing social media, and building partnerships with the university and external companies. Each department coordinates with the team leaders, who set the yearly goals, plan the activities, and choose which events to take part in. The biggest one for us? The European Rover Challenge, which we've been attending since 2022. But why ERC? Because simulating a space mission is incredibly exciting, and the challenge is the perfect place to push our rover passion to the limit by diving into all the different tasks. The last 3 years of experience taught us that ERC is also about realizing that this passion can actually turn into a future job, that teamwork really makes the dream work, and that even rovers can make friends. Basically, there's no reason not to go to ERC. The rover structure and rocker bogie suspension has been studied and tested by the team to be as lightweight as possible while maintaining rigidity and increasing the rover capabilities and modularity. This was possible thanks to the use of welding techniques to eliminate joints, reducing the point of failure. This year, we have decided to focus on developing a new differential bar using a carbon fiber tube and CNC machined aluminum components, drastically reducing the weight while ensuring stability on every terrain. The wheel has also been redesigned, keeping the same dimensions and weight, while removing PLA 3D printed components in exchange for aluminum and high-strength 3D printed thermoplastics, increasing the reliability.
There's more. We are currently developing a new tire prototype using 2 different types of TPU material, printed with a custom honeycomb beam fill to regulate deformation and to increase the capabilities to overcome larger obstacles.
The rover mobility software is based on ROS, using both standard libraries and custom packages. We've relied heavily on simulation to test autonomous feedback and to be able to work even when the rover wasn't physically available. This year, we started migrating from ROS 1 to ROS 2 to stay up to date with community support and ongoing development. Wi-Fi communication on the 5 GHz band combined with the use of ROS enables a secure and reliable multi-device connection between the onboard computer and the control station. This setup ensures that key data, such as rover status and mission progress, is consistently shared. For long-range communication, we use a LoRa module operating at 433 MHz, along with a 5.8 GHz analog video link to provide real-time visual feedback during remote operations. The Rover is powered by LiPo batteries, which supply the necessary energy to operate all onboard systems while ensuring excellent autonomy for completing mission tasks. The power distribution circuit is carefully designed to meet safety requirements and includes 2 emergency buttons. These buttons immediately cut off the power from the batteries, allowing for a complete shutdown of the rover in case of an emergency. Now, what you're seeing here is our testbed prototype, a separate drone we've built specifically to validate software and core functionalities without risking damage to the final competition model. This prototype has allowed us to test autonomous landing using GPS and barometer data and basic flight stability in all directions. Up and down, right, left, backward, forward, it supports manual landing or fail-safe triggered auto landing. For example, here we simulate signal loss, demonstrating the fail-safe in action. The drone will attempt to land approximately where it is. While this prototype handles outdoor testing, our final competition drone is designed for indoor environments where GPS is unreliable. To achieve precision, we've integrated ultrasonic sensor and computer vision. The final frame is a durable 7-inch design with 1300 kV motors, optimized for control and responsiveness. At its core is the Holybro Kakute H7 flat controller, paired with a Raspberry Pi 5 running custom MATLAB and Simulink algorithms for autonomous navigation and precision landing. The final system will follow pre-programmed trajectories and use camera-based detection, like Aruko tags, alongside ultrasonic sensor for centimeter-level accuracy. During the Manipulator design phase, we focused on optimizing the structure and weight distribution. We have completely redesigned the spherical joint, resized the counterweight, and streamlined the entire architecture by removing non-functional supports. The bed drives were revised to improve mechanical efficiency, with a lighter and more compact system. At the same time, using FEM analysis, we have optimized each component to withstand the most critical conditions, improving both efficiency and mass budget. As a result of these optimizations, we've enhanced the dynamic analysis using the MATLAB robotic toolbox and specialized software, simulating realistic trajectories based on the environment and tasks. Thanks to the results obtained from the analysis, the features of the new Manipulator design allow it to perform the final tasks with great precision and maneuverability, ensuring safety within the workspace. Great attention has been given to improving the Manipulator's feedback system. The encoder configuration has been updated, with dual encoders added to each joint to reduce backlash, managed by a new board located on the wrist of the Manipulator. This has improved cable management and, most importantly, responsiveness. Additionally, new cameras have been installed, significantly enhancing visibility during maneuvers, both for the Manipulator and the full rover. The new end effector has been completely redesigned. The gripper, now more compact and effective, provides improved grip and is designed to adapt to the new panel. It will have a performance boost in all other tasks as well, thanks to the new interchangeable fingers with tactile feedback. For soil sample collection, we have based our design on previous subsystems. The deep sampling system uses a DC motor-driven stage to bring a metal tip into the ground and store the sample in a box for weighing. We've studied how to collect samples from various soil types to make the system versatile and reliable.